Right. So today we are going to talk about, I think, what are called partition games. I hope I'm pronouncing that right. The spelling is, oops. Now it'd be great if somebody can just give me a quick confirmation that you can hear me all right and that the screen is visible. This is
Yes,
just
ma'am. Yes, ma'am, we can hear you.
quick sanity check.
Ma'am, can you hear me? We can hear you and see the screen.
Oh, okay. I think Preeti is saying something, but my speaker is probably my speaker volume is down to 0. So sorry, could you repeat whatever you said? Okay. All right. Thanks, Preeti. Yeah. All right. So partition games are a little bit different from all the games that we have seen so far, which, if you recall, we have been calling impartial games. And the reason we have been calling them impartial games is that if I give you a game state, and this could be any abstract game right now, I don't want to specify a specific example, but if you look at a game state, then it doesn't matter which player is playing, they have the exact same set of moves, right? So just as an example, although I said I'm not going to give one, but just as an example, let's look at a game of NIM. Let's say you walk into a room where a couple of players are playing NIM and you don't know whose turn it is. All you see is a bunch of heaps with a bunch of sticks in them. But the set of moves that are available would be the same no matter which player's turn it is. But on the other hand, if you walk into a different room where a game of chess is being played, and you just see two people who are deep in thought and you don't know whose turn it is, but if you think about it and you look at the state of the chessboard, now the moves available to the player who is playing white is different from the set of moves that's available to the player playing black. That's just because of the nature of the game. The rules are such that the player that moves first can only touch the white pieces. The player that moves second can only touch the black pieces, and so on. So that's a classic example of a game that is not impartial. So far we've been looking at analysis for game trees for impartial games, and even the notation of how we expressed a game state and the moves that are available from a game state was relatively simple because the set of moves that was available to either player was exactly the same. So now we need to upgrade our notation and just keep in mind that the set of moves that are available may be different. Okay? So in terms of notation, typically what we are going to do is, normally we said, okay, we're just going to write down. So for instance, if you were using number notation, you may write something like this to denote the, the labels of the games that are available from the current state. So you can say that, okay, if you make a certain move, you go to a game that's in the equivalence class labeled 1, or a state that's associated with the number 1. And here's a different move that will take you to a number 5 game, and so on and so forth. So that was our notation. Now, in this upgraded notation, we are going to have to say something like, for instance, it's just random example here. I haven't fixed any concrete game. So if you say something like this pipe symbol here in the middle is kind of the separation between the left moves and the right moves. Okay, so you have to fix some convention of how you're going to address the players. So left and right is something that's used throughout this book. If you prefer names, I sometimes go by Lata and Raj for L and R, or people sometimes say Alice and Bob if they're using names. Some people like to say first player, second player, but a lot of us do find that confusing because, well, there is, of course, the first player of the global game, But then we also have this thing about the player whose move it is currently, and that could be either the first or the second player of the global game. And sometimes you want to talk about, oh, this is a first player win, this is second player win, without having confusion about whether that's the first player of the whole game or not. So we will refrain from using first and second to refer to the, the global player names. We'll just go with L and R, which is something that seems like a fairly standard and accepted piece of terminology. So what this means is that if it is L's turn, then the moves available to them are given by the states that are written out on the left. And if it's R's turn, then the states available to them or the moves available to them and the resulting states are the ones that are listed on the right. Now, notice that you could also represent an impartial game this way. You just copy paste the collection of states on either side of the pipe. And, it's just that they're always going to be the same, right? Now, you have to sort of upgrade your concepts of what does it mean to be in a winning position? What does it mean to, draw out the game tree? Notice that our game tree now has to be a little more expanded to account for the additional possibilities that come from the different players having different moves. So I do want to talk about all of that, but I feel like that's going to be a slightly longer discussion. So what I want to do today, which is more of a warm-up sort of a discussion, is I want to actually give you a couple of examples of games that you can, hopefully spend some time playing before we meet next, and hopefully develop some just really basic instincts about how partisan games are different from the kinds of games that we have seen so far. So I'm going to give you one board game that might already be sort of familiar from childhood gaming experiences. I'm going to give you one game based on dominoes and one sort of game on a graph kind of a thing. And I think, and let me just confirm, but I think those are the games that we're mostly going to be looking at in this chapter. And of course, the other thing that we want to do is extend our notions of equivalence. Remember, we said two games are equivalent in the impartial setting. If you took a game sum with any third game and they turned out to be in the same outcome class, and this was for any third game J. So that's when you said that G and H are equivalent games. So we want to sort of develop basically the analogous machinery, but in this slightly more general setting, right? So we'll be talking game trees, we'll be talking equivalences, we'll be talking about sums, so all of this good stuff. But for today, I want to have just a relatively sort of constrained discussion where we just talk about 3 rule sets. And I'm not even going to say very much because we don't have the language yet to talk about things. But again, for those of you who are following along with the book does have a lot of exercises just to give you practice with the rule set so that you get familiar with the games themselves. And although it, sounds like you're just playing, I think one thing that does when you start playing the game for its own sake, without worrying too much about strategy or what's going to happen and so on, just try to get some judgment-free experience of playing the game, then you automatically start developing some intuitions around, these are the good moves, these are the bad moves, and so on. And eventually you start, getting to hopefully something that looks like a meaningful strategy that you can reason about. And often, of course, what will happen is that you will go back to the drawing board to account for some missing cases or some possibly mistaken arguments and things like that. But I think the act of actually just playing a game is a pretty useful preliminary thing to do when you encounter a game first. So that was my soapbox and gyan for today. And I'm just trying to justify why I'm going to be leaving you with 3 rule sets. And we'll only come back and develop some of the math next time. However, until we do that, you can also just start thinking about all the notions that we saw in the first couple of discussions that we had, and just think freehand about what should Should this change? Should this adapt? Does this carry over in a natural way? These are all good questions to ask when it comes to partisan games. And I think to be able to make that flow of thought a little bit easier, I think it helps to have some concrete examples. So let's start with what is called, again, I'm not sure if I'm completely butchering the pronunciation here, but I think it's called Conan. This is apparently a Hawaiian game, which looks similar to, well, at least to me, it looks similar to marbles, but then the book claims that it's also similar to checkers because it has these black and white pieces, which are placed in an alternating fashion. So let me actually see if I can pull up the picture from the book into the notes, which will be faster. All right, that's taking a little bit longer than usual. We'll just try again. Okay, that seemed to work. All right, so as you can see, you have a board here where the locations have black and white tokens on them, or black and white stones. And you can see that they're sort of placed in an alternating fashion, as in you have the black tokens surrounded by white tokens and so on. But you'll also notice that there are these two gaps somewhere out there in the center. And those gaps will be useful for actually making your moves, right? So what are the moves? So on your turn, you essentially use one of your stones. So, let's say you're playing black. You'll have to use one of the black stones to jump over a white stone and reach an empty spot. Okay. And you cannot jump diagonally, although I'm not sure if, at least to begin with, I don't think we have diagonally adjacent black and white pieces because the diagonals just go like that. So the diagonals are right here. So I think in the beginning, the question doesn't arise. You're going to be basically jumping over an orthogonally adjacent white token. But that's essentially what you do. So you could take your piece here and shift it here. Okay. And this is the sense in which I was saying that this reminds me of marbles, because that's the fundamental move in marble, except that, I mean, if you played marbles, this should make sense. So you jump over another stone to an orthogonally adjacent empty location. So up to there, I think the move is exactly the same. In marbles, you additionally remove the stone that you jumped over, and your goal is to clear the board. So it's a single player game in some sense. And here, as far as I can tell, you don't touch the other player stones. You just keep moving, right? Now, also the other sort of aspect of this is that if you have an empty space along the same line and another white piece, so if you had, for instance, a white token here, and let's assume for a moment that this was an empty space, then you can keep going with your jumps if you would like, right? So one thing that we do here is essentially talk about, okay, just give me 1 second. As usual, my iPad here is acting up a little bit. All right, so yeah, I think this is now fixed. Sorry, I think screen was frozen for a bit. Okay, so like I said, the moves. Okay, so let me just recap what we just said here. So the game state is a board with black and white pieces which alternate. Plus, there are two empty locations initially to facilitate movement. And all right, so I should say that there's a version of this where the alternating part is optional. So I think that's called generalized Conan or whatever. And on your move, what you can do is, so this is the initial state of the board. And on your move, what you can do is, okay, let me actually, it's easier for me to denote the pieces as green and blue, or maybe red and green here. So you have a red piece and a green piece. And let's say that we have an empty location after this. Then it's what you can do on your turn is to basically pop over the opponent's piece. And if you have another opponent piece here, I shouldn't have probably that. Let me illustrate this in this fashion. Okay, so if you have a bunch of alternating empty and opponent piece locations, then this jumping can continue. So you can do this until you're stuck. And of course, if it's strategically better for some reason, you might actually pause somewhere in the middle. Okay. So I also did say that you don't have removals, but actually I should take that back. I think my initial interpretation was that you basically do your movements until you have some sort of a segregation, at which point you have no moves left. But I think realize that these moves are called captures. Here. So if you make that move, then this is a capture, and that's just like, so I just noticed that this is called, this is literally called Hawaiian checkers, and this is analogous to how moves work in checkers, where your moves are designed to capture opponent pieces. And your goal is to basically be in a situation where, just like we've been doing with our impartial games, you're stuck with no moves remaining. And well, your goal is to make sure that your opponent is stuck with no moves remaining, because that's when they end up losing the game. So so you could look at, for instance, the simplest sort of a position would be if you have, let's say, two adjacent pieces. Let's say you have a green piece and a red piece next to each other. And if you want to denote this position, then notice that these are positions where you kind of go, well, if you assuming you have orthogonally adjacent empty squares, the player whose turn it is the player who is able to make the move, and you're, thereafter you're kind of stuck, right? So that's sort of the simplest instance of a Conan game, and there are a few more instances in the exercises for you to play around with and sort of experiment and see how that goes. Okay, so that's our first rule set. I am wondering about the segregation version. My potential concern with a segregation version where you don't perform captures and you basically get stuck when there are no legal moves left is that you can probably come up with configurations where, because the pieces are always there persistently on the board, that you might end up, or it's possible to enforce a gameplay that just repeats configurations and moves in cycles, which probably makes for a less interesting game. Okay, so that's a couple of additional remarks about Hawaiian checkers, if you like. Now, which, well, this is a game where players take turns to color the nodes of a graph red or blue. And the only rule is that you cannot color two adjacent vertices the same color. So let's say that the first player L uses the color red and the second player R uses the color blue. So let me go over a sample gameplay here. So for instance, let's say the first player colors this vertex red. The second player can color, for example, this vertex blue. Now, if you go back to the first player, they cannot color this vertex red because that would make for two adjacent red vertices. So they have two choices. They could either color this vertex red or this one. But notice that if you color this vertex red, then you actually give the blue player one more move, whereas, and after which you get stuck actually, because you have no valid moves left. And so that would take you to a losing game. On the other hand, if you choose to color this vertex red, notice that now the blue player is the one who is stuck because both of these would not be valid moves. Both of the vertices are now adjacent to the only blue vertex. So this is a game that the first player ends up winning. Okay. And if you have like an absolutely general graph, then these it does turn out to be a little hard to predict who has a win. But a good exercise for games like this is to say, you know, what if your graph was just a path? Who has a win? Or what if your graph was a star, for instance? This one is sort of easy because if you take the as the first player, if you take the central vertex, then the second player is free to choose one of these because there are no blue vertices yet. And now notice that the first player is stuck. So it's not a wise move to start with the center. So you want to get to one of the leaves. This blocks the center. You cannot pick the central vertex anymore. By the way, by the center, hopefully it's clear that I'm referring to this vertex. Now, as far as the other player is concerned, if they want to continue being in the game, then they should also not pick the center for the same reason, because they're going to be stuck in the next to next move. They'll have nothing more left to play. So essentially, both players are incentivized to keep going on the vertices that we're going to call the leaves, because this is just a tree with, you know, one vertex in the middle and n-1 leaves if there are n vertices in total. And you can imagine where this is going. If the number of leaves is even, then you can see that the red player is the one who is going to get stuck. And if it's odd, then it's going to be the blue player, right? So then that's what's going to happen on this very simplistic sort of a tree. What if you had one more layer further down? That's something worth thinking about. And if there are other simple kinds of graphs that you can think of, so for instance, you could also think about what happens if you had a cycle rather than a path, and so on. And gameplay is just, you know, the users. So in all of these games, the winning rule is the same. The player who gets stuck first is the player who loses. So that's just what we call normal play before. That's going to also be true of the last game that we are going to see, which is called Toppling Dominoes. Again, for now, at least, I won't have more to say about the graph coloring game. The book, of course, analyzes it a little bit more because by now they have developed some language to talk about game trees and so on. But you can still make sense of some of the exercises, which just ask you to analyze instances of coloring with some pre-colored vertices. a couple of steps further from the game state that's given to you. Now the okay, now I want to talk about, so before I talk about the next game, I do want to say that for graph coloring, please look at the PDF version of the book and not a printout, in case you have a printout, because all the vertices are pretty much rendered black and white, and that makes it hard to figure out what game states we're working with. So which are colored red, blue, and green. Actually, let me see if I can do this trick again of pulling up a screenshot. So green is sort of it's worth thinking of green as some sort of a neutral color, whereas red and blue are the colors that are associated with the players, just like we had in graph coloring, right? So good. We have a sequence of dominoes, as you can see here. Now, in this particular example, we appear to not have green dominoes specifically, but let's say that that's the general state of the game. Now, on your turn, you can pick a green domino, which is a neutral domino, or you can pick a domino that's your color. So if you're a red player, you can choose a red domino. If you're the blue player, you can pick a blue domino, right? And then you choose to topple, right? And what happens is that the dominoes in the that are present in the chosen direction, left or right, are basically removed from play. Okay, so here, for instance, we have, well, this is what is left. So we're probably looking at this portion of the original instance. So what must have happened is that we picked this domino. So the first player in this case is going blue. So if you pick this domino, which is indeed, okay, as is pointed out here, the fourth domino from the right thing is basically going to knock over these fellows. And that's what you have left here. And now the other player doesn't have much of a choice, in the sense that there's only one red domino on the board. So that's what you have to topple. And at this point, the situation is more or less symmetric, because you could topple to the left or the right, be left with the same state. So essentially, you basically have to figure out which piece you want to work with, and which direction you want the toppling to happen. Okay, and there are variations of this where the only dominoes that will topple are the dominoes of the opposite color or of your color, and typically the neutral dominoes get toppled over anyways. So there are definitely some more complex variations on dominoes, where the dominoes may not even be on a line, but they may be even on a more general sort of a layout. But for now, I think this is a good, this is sort of a good game to sort of start with. Again, in each of these cases, what I think is a good exercise to do is look at some really simple instances of the game, and start thinking about, well, what would you do if you were the first player? How would you respond if the other player made this move? Those are good questions to ask. And eventually, of course, even for the smaller states especially, you do want to know if one of the players can force a win, and think about what does it mean in the partition setting for a player to force a win. Do you have to think a little more compared to, say, what we have had going so far for the impartial games and so on. Okay, so now I think I've rambled on for a while, so I will stop here with these three rule sets for you, starting from Hawaiian checkers, then graph coloring, and finally toppling dominoes. By the way, in graph coloring, if you know graph terminology, then essentially both players are trying to maintain an independent set of their own color. that's what is happening. But you also have variations of this. Of course, you're looking at a vertex picking version of the game here. You could also be picking edges. But an important variation, even in the vertex picking version, is that you're trying to maintain a global independent set. So there's no, in some sense, there's no colors associated with the players. It's just that every vertex is either colored or uncolored. And on your turn, you're trying to add a vertex to the set of colored vertices in such a way that the colored vertices induce an independent set, like no two colored vertices are adjacent. So there's no red or blue. You're just trying to collectively build an independent set. And again, in all of this, it's not at all obvious what a winning strategy should be or which graphs are winning for the first player. And those are all legitimate questions to ask. There are also good computational questions that you can ask. You can ask what's the complexity of deriving a strategy. So for instance, even for Hawaiian checkers, I think the complexity status is pretty challenging in the sense that I think this is an example of what you would call a piece-based complete game and so on. But that's just a side remark. We will be coming back in the second half of these discussions to talk almost exclusively about computational aspects. So I don't want to go on those sort of tangents right now. What we will do instead is continue focusing on the game trees, developing the concepts of winning positions, talking about game sums and equivalence classes. So that's what's coming up over the next couple of days. And yeah, that's pretty much what I have for now. This is just a quick logistics note. This is shifting week for me. I'll be a little bit distracted with moving offices. So we might actually put this on hold until I am done with the move. So most likely we should be able to resume in 2 or 3 days, but I will basically put the series on pause until further notice in the group. So please watch out on the group for announcements. Hopefully we'll be able to resume later this week, and maybe we can do the Sunday meeting if we would like to make up for time. But on the other hand, we are just mostly having fun. So I would say use the time to maybe take a sneak peek at what's coming up, look at the exercises in the book, play these games, develop some intuition, and let's come back in a little bit to talk more. But just in case I'm delayed further, I will keep everybody posted in the group. So I hope that's fine. All right. So with that, it's a wrap for now. Let me stop my share here and the stream as well. And of course,